So we've been pulling pretty hard from Newton's second law recently, so it'll be a nice change of pace to pull from another one for this concept. Imagine you and a friend are floating side by side in space where there are no forces acting on either of you at all. If you push against your friend, Newton's third law says that their body exerts an equal and opposite force back on you, and so you both end up floating backwards, away from each other. We have two forces happening, A on B and B on A. A on B, we can say, right, we can now write force in our new momentum way. It's dP it's the momentum of B as it changes with time. And the force B on A, we can write as the change in A's momentum with respect to time. Okay? Since the forces are equal and opposite, then FA on B is equal to FB on A. Well, it's equal to the negative. And so then therefore FA on B plus FB on A is equal to 0. Seems trivial, but this is an important concept. So written in our momentum form, dP, the change in momentum of B with respect to time, plus the change in momentum of A with respect to time is equal to 0. And if these are the only two particles or bodies in our system, then PB plus PA is the momentum, the total momentum of our system. We'll call that capital P, the total momentum of our system. And so then we can say that dt of PB plus PA equals 0, and thus the capital P momentum of our whole system with respect to time is 0. So the time rate of change of the total momentum, P, is 0. In other words, the total momentum of the system is constant, even though the momentum of each person is changing. Forces that are exerted by particles within the system are called internal forces, and forces exerted by particles outside the system are called external forces. A system which is isolated from any external forces is called an isolated system. What we've come up with is that momentum is conserved for any isolated system. If a system is not isolated and it has external forces, then momentum is not necessarily conserved. But if we consider the whole universe as our system, it is isolated and momentum is conserved. So here's the principle of conservation of momentum in words. If the vector sum of the external forces on a system is 0, the total momentum of the system is constant. What makes this useful is that we don't have to know much about the actual forces going on in order to find out a lot about what's going on. Say we have an isolated system with 3 bodies, A, B, and C. At any given moment, they have individual momenta of, so the momentum of A is equal to MA VA, A, and the momentum of B is the mass of B times the velocity of B, and the momentum of C is equal to the mass of C times the velocity of C. So that's their individual momentum. And together, considering the system as a whole, the system of these 3 particles, the sum equals the system's entire momentum. So the total momentum for the system, P, is just the vector sum of these. So VA plus MB, VB plus MC, VC, and so on if you had more particles. So just like we did with conservation of energy, we're going to exploit this by picking critical points in a scenario to find individual momenta, while knowing that the total momentum of the system is equal at each point.